Okay, hi. Now we go to slide number 41 and talking about ionic lattice have an ordered structure. If we talked about the sodium chloride, and if we see the sodium chloride here, and we can see the sodium is small in atom, chlorine is big, and the lattice or the sodium crystal consists of not as we know as NaCl, that's it, but in the unit cell, we call it a unit cell. How many sodium and chlorine in a unit cell? Is it only one sodium, one chlorine? No. It should be, it's usually we have sodium, it's on the corners here. If you see the crystal structure, we can see some corners have sodium, the other corners of the lattice, we call the lattice or the crystal, we have chlorine. So as I can count here, 1, 2, 3, 4, 4 sodium, and we have 1, 2, 3, and where's the number 4? The chlorine should be there. So 4 by 4, and it's repeated in another crystal beside it. And you can see the lattice is like that. Between the minus and plus charge, there's a bond. And this is, we call it ionic bond. And because the sodium lost the one electron in the outer shell to the chlorine, and chlorine gained this electron and became minus charge, or have an extra of 1 electron. Of course, there will be a bond between them, and that bond will create a structure, and depends on how many NaCl in the unit cell, in the 1 unit cell. So we have to consider that it's not only 1 NaCl in the cube or in the structure of 1 unit cell. The one, what does it mean, 1 unit cell? One unit cell is the smallest cell can form the molecule, is the smallest. So what is the smallest? Okay, what's the smallest molecule of the salt? We say NaCl. 1 Na, 1 Cl. But what is the smallest number of atoms in the 1 unit cell? Here we have to go back to the crystal structure and see there is 1 unit cell consists of 4 chlorine, 4 sodium, and it is repeated for the next crystal. And see there is a lattice when there are too many or millions, billions of unit cells, one beside one. And here, if we come to the 11 electron of the sodium. So the sodium atom has 11 electrons, can lose 1 electron to become sodium plus ion. So positive charge of the sodium because it's lost 1 electron. And it will enter the lattice inside. Whereas the chlorine, 17 electrons gained 1 electron to become 18 electrons and enter the lattice. So the lattice consists of too many, or the similar number of chlorine with a similar number of sodium in 1 unit cell, and it is the sodium chloride salt. So what does it mean, ionic lattice? So it's the common structures type adopted by ionic compounds of general formula. So there is a formula for this lattice or different lattices, either consist of 1 atom and the other one different. So they are heterodiatomic, or there is mx2, whereas there is 1 atom and the 2 other atoms, or there is m2x, and so on. So such structures are usually determined by X-ray diffraction methods. So that's how we can find the crystal structure of and what is the type of the lattice inside this crystal, so we can find it or obtain it from the X-ray crystal structure. Now, what's the different ions scatter X-rays to differing extents depending on the total number of electrons in the ion, but the ray has limitation, like the location of the light atoms of hydrogen in the presence of much heavier atoms is difficult and sometimes impossible. So the X-ray crystal structure, it's easy to measure the small lattices, whereas the big lattice, we need to use different analysis or crystallography method, not or other than X-ray, because X-ray determine the small lattices where there is a small amount of atoms. So neutron diffraction, in which neutrons are diffracted by nuclei, may be used as a complementary technique. So there is another method to measure or find the lattice. For the bigger molecules, we can use neutron diffraction array. So that's the diffraction between the neutrons diffracted by the nuclei or inside the nuclei. So now what's happening? How can we measure the X-ray? Comes from the machine, hits the atom goes to the excited states, and then when it comes back, reflect or scatter the X-ray, and then there is a film here to attach, and then it will record or draw the structure of the shadow of each atom on the film. Okay, we have the structure of the rock salt. That's in nature, we can find the rock salt NaCl lattice in the halite, which is the formula is MX type of lattice in halite. So halite is an ore which contains the salt NaCl, very pure in the nature, formed naturally as a cubic crystals. So cubic crystals, this is 1 unit cell. As I said, there are like the smallest one, if we go to the face side, and this is, you see the bigger unit cell of the halite, and we can see at the corners, we have the chloride atoms, and in the middle, small one, the blue one, is the sodium atoms. So as you see here, we mentioned that if we have 1 chlorine in the center, 4 at the corners, at this face site, 5 chlorine, 4 sodium. The other side here is the similar, and there is bonds between them, and they are forming the crystal lattice. We have a zinc blend. Again, this is zinc blend. The ratio coordination may be MX2 1:2 or MX 1:1 ratio. Every other side, the diamond type array is occupied by either zinc or sulfur centers. So this is the zinc blend, and we can see the lattice. For the 1 unit cell, you can see the zinc in red and the sulfur in blue. So the zinc blend, thermodynamically favored at 298 Kelvin, can slowly transform to quartzite, and both are polymorphs. Likewise, diamond can go graphite transition. So we have diamond and we have graphite. So if you change the structure of the molecule, the unit cell, you can end up either with a diamond or you can end up with powder of graphite. So see, the diamond is very expensive because of the it's pure. It will be very solid, not easy to break, and the diamond used in industry to cut other metals, and has many useful things in the like buy and sell trading, whereas the graphite used in the pencils tips, and we can draw with it with the graphite, which is very cheap. So the crystal structure can determine the value of that compound. So the salt formula could be like calcium fluoride 1 to 2. So 1 calcium, 2 fluoride. So we can go with MX2 as a type of lattice. So we can you like as a summary knowledge, you can take the MgO, magnesium oxide, adopts NaCl lattice, the similar lattice. Why? Because it's 1-to-1 ratio and it's look like salt. How many magnesium and oxygen ions are present per unit cell? So per unit cell, it should be, because of the oxygen -2, magnesium lose or lost 2 electrons to the oxygen, so it should be 1-to-1 molar ratio. Other lattice is beta cristobalite, silicon oxide, rutile, titanium oxide, occurs in granite rocks. There is C, cadmium iodide, cadmium chloride. All these are lattices. You see the structure. They are differ from one to another, and it's very important for the X-ray or for the pure drugs and these things. Okay. Now we can go to the lattice energy. We estimate from the electrostatic model, as I consider their point charge mz plus and xz minus. So we can determine or find out the energy of the lattice. Depend on the mx. M is the metal, X is the halogen maybe, or the other one. So the lattice energy delta U, 0 Kelvin of ionic compound, is the change in internal energy that accompanies the formation of 1 mole of the solid from its gas phase ion at 0 Kelvin. So if we go for the M, we don't know how many plus charges there in the gas phase, plus how many halogens gained negative charge in gas, and this will form MXN as a solid. So how many, what's the ratio between M and X? So that will differ. Calculated lattice energy and experimental energy must be considered. So if we come to the summary knowledge or self-study, can you write the chemical formula of beta cristobalite, zinc blend, rutile, cesium chloride, and fluoride? So you can come back to the previous slides and you can find out what's the structure formula for these ores or the salts. So define the lattice energy and define halite. What is halite? What does it mean? Polymorphs. Give 2 examples. Determine the number of formula units of calcium and these things. Structures of ionic solids. So in these ionic solids, The ionic of metallic compounds possess order arrays, automatic arrangement, form crystalline materials with lattice structures. Structure of ionic solids. So the packing of the spherical atoms or ions must be considered. However, the difference in bonding result in distinct properties of these solids. In metals, the bonding is essentially covalent in metals. When there is a pure metal, so there is a covalent bond. And the bonding electrons are delocalized over the whole crystal, giving high electron conductivity that is characterized for metals. So as you know, that if we have like 1 gram of iron, it's only pure iron. So this 1 gram consists only of multiple or millions of iron atoms. So these irons bonded to each other in a covalent bond. So covalent bond, when there is only pure atom, same atom, homonuclear atoms, they can bond to each other covalently. So, and how the electrons move, they move all over the structure, and they are moving at the clouds. There is no gain and loss, only these electrons, the last final covalent electrons of the final orbitals, they can move on each other and making clouds around the metals as a whole. So ionic bonding in the solid state came from the electrostatic interaction between the charged ions. So differently will happen with the ionic bonding. Ionic bonding, we have losing charge, we have gaining charge. So there will be positive and there will be negative. So here, positive and negative will form ionic bonds. Packing of spheres. So how can these atoms be arranged or packed in the solid state? The atoms introduced in a unit cell and interstitial or separation hole. So now we are talking about the packing, or what types of packing we have, what types of structures, crystal structure we have to consider cubic and hexagonal close packing. So if you're replacing a number of equal sized spheres or balls in rectangular box in a specific arrangement, you will see the figure called close packing. So this is the close packing, which is replacing number of equal size spheres in a rectangular box in a specific arrangement. So this is the close packing. So spheres that are not on the edges in the assembly are in contact with 6 other spheres within the layer, hexagon shape is produced. So there is a hexagonal shape. Hollows between the spheres allow building another layer of spheres. So there is like spaces. Hollows are spaces between the atoms, so can make other building up layers. And a second close packing being achieved. So there is a first close packing. There is inside or next will be the second close packing, and so on. Third close packing could be arranged differently. So the arrangement can be extended sideways as well. So you can the arrangement can go sideways or up and down. The sequence of layers can be repeated. So 2 repeated close packing layers can be like AB, 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 while the second contains the 3 repeating like ABC, ABC, ABC. So now we have layers. If these layers are repeated for the first one, you can see layer of A, B. So A is the first atom, B is the second. Then will come A and B, A and B. And by repeating this, that will do the first layer. Maybe there is another layers contains of 3 atoms, can go ABC, 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 and so on, repeatedly. So the AB called cubic close packing, CCP. That's where is the 2 atoms and repeated in the layers, they will do cubic close packing, or we call it CCP. And there is ABC called hexagonal close packing. Hexagonal. So here we can have like 4, here we have 6. So hexagonal will do HCP arrangement. So in each structure, given sphere is surrounded or touched by 12 other spheres, and it is said that it has the 12 nearest neighbors to have coordination of 12 coordinates. And here we can see how can layer of A formed in red sphere in close packing, and then if you add another layer sideways in yellow, or you can repeat A layer on the above of this will come here in red, and then what will come after that? Yellow. So there will be red, yellow, red, yellow, red, yellow. These layers are cubic, CCP. But if you add third layer, if you make the first layer and second, and you add blue layer, so you are doing the first layers of A, B, C. And then you repeat another layer of red on the top of blue, and yellow and blue, red, blue, yellow, blue, red, yellow, blue. This will be 3 layers, different atoms. We call it HCP, hexagonal. So this is the unit cell cubic for the salt, face centered in the lattice. Here is the hexagonal layers or structure, and you can see here is the hexagonal in different shapes. Okay, then we can go to the application of close packing arrangement. We can see in the gas of hydrogen transform to liquid at 20 Kelvin and to solid at 14 Kelvin. In the solid state, these diatomic spheres spheres can be represented by HCP arrangement. Fluorine, difluorine, solid at 53 Kelvin, but can be cooled down at 45. A phase change to give a distorted, not exactly close packing structure. So there is a distortion in the close packing, could happen for some structures. Metallic elements, titanium, manganese, cobalt, nickel, are solid by itself at 298 Kelvin, which is room temperature. However, many metals are polymorphic and can have more than one structure depending on the temperature. So now we come to the monomorph. It means have only one structure, whereas the polymorphic compounds, they have different, more than one structure. It depends on the temperature. So self exercise, or we can go summary knowledge. A summary knowledge here, we can see you can do what's the definition of close packing, CCP, HCP, and so on. you can come back here and see exactly what are these names came from. Okay, so now common anions found combination with group 1 and 2. We stop here.